This is the first of several lectures on gravitational waves. The exciting thing about gravitational waves is that they allow us to make direct observations of strongly gravitating systems. As you probably know, we have a growing network of ground-based gravitational wave detectors that have recently detected a number of collisions among black holes and neutron stars. The first gravitational wave detection occurred in September of 2015. This event consisted of two black holes orbiting each other, then spiraling together and merging to form a single black hole. Now, this system originally consisted of a 36 solar mass black hole and a 29 solar mass black hole, and they merged to form a 62 solar mass black hole, plus about 3 solar masses worth of gravitational waves. So let me complete my picture here by showing some gravitational waves. This first detection was made by the LIGO detectors, which are in the United States. There are actually two detectors, one in the state of Washington, which is in the northwestern part of the country, and the other is in the state of Louisiana, which is in the south central part of the country. Since this time, there have been a number of other detections. One of the most notable occurred in August of 2017. This was a 25 solar mass black hole merging with a 30 solar mass black hole. And this was seen not only by the two LIGO detectors, but also by the Virgo detector, which is located in Italy. Then just a few days later, also in August of 2017, the two LIGO detectors and the Virgo detector detected a binary neutron star merger. And this event was also seen in the electromagnetic spectrum as a gamma ray burst. In addition to the LIGO and Virgo detectors, there are a number of other detectors around the world that were not sensitive enough to see any of these events, and they probably won't see any future events either. But these instruments have played an important role in the development of the technology needed to detect gravitational waves. Among these other detectors, the most notable are GEO in Germany and TAMA in Japan. Currently, plans are underway for the construction of several new detectors whose sensitivities will equal or exceed the sensitivities of the current LIGO and Virgo detectors. These new detectors include Kagra, which is in Japan and might be online as early as 2020, and Indigo, which is in India, and construction is expected to begin around 2020. There's also a lot of interest and serious discussions about placing a gravitational wave detector in Australia in the near future. Now, all of these detectors that I've mentioned so far are ground-based instruments. They're large-scale interferometers, They have arm lengths in the range of 3 to 4 kilometers, and their sensitivities are in the range of tens to thousands of hertz. So these instruments are all sensitive to the gravitational waves from events like the merger of approximately equal mass black holes or neutron stars. One of the most exciting plans for gravitational wave physics is the LISA mission, which will place a gravitational wave detector in space. So this is the LISA mission. It's being led by the European Space Agency with input also from NASA in the United States. Now the LISA detector will consist of satellites working together as a large interferometer with arm lengths of millions of kilometers and a sensitivity in the range from 10 to the minus 4 to 10 to the minus 1 hertz. This is the appropriate frequency range for an event such as the in-spiral of a roughly solar mass black hole or neutron star into a supermassive black hole. Currently, the expected launch date for the LISA mission is around 2034. So what is a gravitational wave? I don't have a simple one-sentence answer to that question, but in a few sentences, it's a fluctuation in the curvature of space-time It produces oscillatory tidal effects So these are the world lines of two freely falling particles. These particles are unaccelerated, but the space in between them is expanding and contracting due to the passing gravitational wave. And finally, I would add to this description that the fluctuations propagate through space at the speed of light. Now, gravitational waves are a bit complicated to describe mathematically, and this is for two main reasons. The first reason is the Einstein equations are nonlinear. As a result, we can't write down exact solutions in most cases. We have to work with solutions that are only approximate. And another consequence of the nonlinearity is that waves can't be superimposed. But what we can do, in spite of this nonlinearity, is develop the theory of weak waves as small perturbations of flat spacetime. So weak gravitational waves as perturbations on flat spacetime. And this should be sufficient for applications in astrophysics where the gravitational waves we detect from distant cosmological events are very, very weak. So this is okay for applications in astrophysics. Now, the second main reason why gravitational wave theory is complicated is because general relativity contains a large gauge freedom. Now, what I mean by gauge freedom in this context is the freedom to change space-time coordinates. So a change of space-time coordinates doesn't actually change the space-time geometry. The term gauge comes from electromagnetism, and it's also used in Yang-Mills theories in particle physics. And in this context of gravitational wave physics, we often refer to this freedom of changing space-time coordinates as a gauge freedom. In practice, this is an important issue because we need to know how to interpret the metric to understand whether fluctuations are coming from the space-time geometry or from the choice of coordinates. So fluctuations in the metric could be coming from the geometry or from the choice of coordinates. Or, of course, a mixture of both. Let me give you an example of this. Let's take flat space-time in Minkowski coordinates. So let's let those coordinates be t bar, x bar, y bar, and z bar. So the metric is minus dt bar squared plus dx bar squared plus dy bar squared plus dz bar squared. And now let's make a change of coordinates. So the new coordinates are defined by t bar equals t, x bar equals x, y bar equals y, and z bar equals z minus a divided by omega times cosine of omega times t minus z. In this expression, omega is an angular frequency and a is an amplitude. It's a dimensionless amplitude, and we want to think of this as being very small. So this coordinate transformation is close to the identity. Now let's work out the metric in these new unbarred coordinates. We have ds squared equals minus dt bar squared, but t bar is equal to t, so this is just minus dt squared. Likewise, we have plus dx squared plus dy squared plus dz bar is dz plus a times sine of omega times t minus z times dt minus dz, and all of that is squared. Now let's simplify this. We have minus dt squared plus dx squared plus dy squared. Then squaring this term, we have dz squared. We have the cross terms, which are 2a times sine of omega t minus z times dz times dt minus dz. And then we have the term that comes from squaring this term, and that term is proportional to a squared. And remember, a is very small, so we'll drop these terms. So putting this together, we have minus dt squared plus dx squared plus dy squared plus, now the dz squared terms, we have 1 times dz squared minus 2a sine of omega t minus z times dz squared. And then we also have these terms dz times dt. That's plus 2a sine omega t minus z times dt dz. And there are higher order terms in a that we're dropping. Now because a is small, this metric is close to the Minkowski metric, fact, we can write the metric as eta mu nu plus a small perturbation, which we'll call h mu nu. So h is a perturbation of the Minkowski metric, which is proportional to the small amplitude a. Let me write down h explicitly. From the line element here, we have h mu nu as a matrix equals 0, 0, 0, a sine of omega t minus z. And the second row is all zeros. The third row is all zeros. And we have a times sine of omega t minus z, 0, 0, and finally minus 2a times sine of omega t minus z. So this metric looks a lot like what one might think of as a gravitational wave, but it's not a gravitational wave. It's not. The oscillations in the metric are just coming from oscillations in the coordinates. Remember, this is just flat space-time written in a new set of coordinates. We can see what's happening if we recall the coordinate transformation was z bar equals z minus a over omega times cosine of omega times t minus z. And now remember, t was equal to t bar, so we can also write this as t bar minus z. And in this expression, z bar and t bar are Minkowski coordinates for flat space-time. So if we plot a Minkowski diagram, this is the t bar axis, and this is the z bar axis. Then the curves of the constant z bar are, of course, just straight lines. So this is constant z bar. Now, what about the curves of constant z? For example, let's take z equals 0 and plot that curve on this t bar z bar diagram. So if z is equal to 0, there's 0 here, 0 here, we have z bar at t bar equals 0, z bar is minus a over omega. So right here, and then as t bar increases, we get a sine or cosine wave like this. So this is the z equals 0 curve. Now let's pick another value of z, say pi over 2. So we start shifted to the right by pi over 2 and also shifted in phase upward by pi over 2. So that curve would look something like this. So this is the pi over 2 curve. So the lesson from this example is that we need to be careful. This metric with this perturbation on flat space-time is not a gravitational wave. The wave-like elements in this perturbation just come from a choice of wavy coordinates. In later lessons, I'll go through the analysis of the gauge freedom for perturbations on flat space-time and show how we can restrict the choice of coordinates to eliminate solutions like this one. For now, I think it will be useful to put these issues aside and show you a metric perturbation that does represent a gravitational wave. So here's the example that I want to use. The metric is close to flat space-time with Minkowski coordinates, and the perturbation is h mu nu. And h mu nu written as a matrix is 0, 0, 0, 0, 0 times a sine of omega t minus z, 0, 0, 0, 0, then minus a sine of omega t minus z, 0, and then the last row is all zeros. This metric represents a plane wave propagating in the z direction. Now this dimensionless amplitude A we're assuming is small, much smaller than 1. And you can check that this metric satisfies the vacuum Einstein equations. So that would be g mu nu equals 0 up to through linear order in A. So there are then error terms of order A squared. So that just means this is an approximate solution of Einstein's equations, not an exact solution. Now the first thing I'd like to do with this metric is to compute the geodesic equations. For that purpose we need the Christoffel symbols. So gamma, mu, alpha, beta is 1/2 g upper mu nu partial alpha g beta nu plus partial beta g alpha nu minus partial nu g alpha beta. So we're going to need the inverse metric. What is that? Well, let's recall the metric itself is the flat metric plus a perturbation h. So we expect the inverse metric to also be close to the flat metric. So g mu nu is eta mu nu plus some small perturbation, let's call it k upper mu nu. And now we want to define k such that g mu nu g upper nu sigma is equal to delta sigma mu. So let's work that out. That's g mu nu plus h mu nu times eta upper nu sigma plus k nu sigma. And now eta times eta gives delta mu sigma. We have a term eta times k, that's eta mu nu k nu sigma. We have this term h times eta, h mu nu eta nu sigma. And then we have a term h times k, but that's second order in small quantities. So we'll ignore that term. And now all of this must equal delta mu sigma, so that tells us that eta mu nu k nu sigma equals minus h mu nu eta nu sigma. And now if we multiply this equation by the inverse of eta, say eta rho mu, so we're multiplying this equation by eta rho mu, we find k rho sigma equals minus eta rho mu h mu nu eta nu sigma. So this is k, the perturbation of the inverse metric. And for notational convenience, we're going to define this combination, eta inverse times h times eta inverse, as, well, here's the minus sign, as h upper rho sigma. So here I'm using for the first time the convention that indices on h, the metric perturbation, are raised and lowered with the flat metric, with eta and its inverse. So now we can write the inverse metric as eta mu nu minus h mu nu. And notice also when we insert the metric in here, all the terms involving derivatives of eta vanish. So the Christoffel symbols become gamma mu alpha beta equals 1/2 eta mu nu minus h mu nu times partial alpha h beta nu plus partial beta h alpha nu minus partial nu h alpha beta. For now, we're just carrying out our calculations to linear order in small quantities. Remember, h is proportional to the small amplitude a, and so also derivatives of h are small quantities. So in this expression, h times derivatives of h are of second order, and we'll ignore those terms. So we'll write gamma equals 1/2 eta mu nu partial alpha h beta nu plus partial beta h alpha nu minus partial nu h alpha beta. Then there are second order terms that we'll ignore. Now let's recall that the only non-zero components of h are hxx, which was equal to a times sine of omega t minus z, and that was also equal to minus hyy. And all the other components of h are zero. So when we compute the Christoffel symbols, the only possible answers we can have are either 0 or plus or minus 1/2 times the derivative of this function. So let me just skip to the results. The Christoffel symbols that equal plus 1/2 a omega times cosine of omega t minus z are gamma txx, gamma zxx, gamma xtx, and gamma yzy, and of course also gamma x, xt, gamma y, yz, since the Christoffel symbols are symmetric in their lower indices. And the Christoffel symbols that are equal to minus this same quantity are gamma t yy, gamma z yy, gamma x zx, and gamma y ty, and all the other Christoffel symbols vanish. And now for the geodesic equations. Remember, the geodesic equation is x mu double dot plus gamma mu alpha beta x dot alpha x dot beta equals 0. So for the 0 component, or t component, we have t double dot plus, we have the non-zero Christoffel symbols with an upper t index, that's txx and tyy. So if we insert those in here, we obtain 1/2 a omega times cosine of omega t minus z times x dot squared minus y dot squared, and that's equal to 0. For the x component, we have x double dot plus a omega times cosine of omega t minus z times the non-zero Christoffel symbols have lower indices tx and zx, so this is times t dot x dot minus z dot x dot equals 0. For the y component, that's y double dot plus a omega cosine of omega t minus z times z dot y dot minus t dot y dot equals 0. And finally, for the z component, we have z double dot plus 1/2 a omega times cosine of omega t minus z times x dot squared minus y dot squared equals 0. So these equations are fairly complicated, but there's one family of solutions that is fairly easy to identify. And it's the following. Remember, dot stands for derivative with respect to proper time. So one solution is t equals tau, proper time, x equals x naught, some constant, y equals y naught, and z equals z naught, where these are all constants. And of course, we could add a constant to tau here as well. You can verify just by inspection that these world lines satisfy the geodesic equations. So all of these terms with double dot vanish, and also all of these other terms are proportional to at least one factor of x dot, y dot, or z dot, so they all vanish as well. Let me draw a picture of these world lines. So here's the t-axis, y-axis, and the z-axis. So I've suppressed the x-axis. Each of these world lines is at a constant value of x, y, z, and just runs parallel to the t-axis. So this is the family of geodesics. Each one of these geodesics has a 4-velocity x dot mu, which is 1, 0, 0, 0. This might seem like a strange result. After all, there's supposed to be a gravitational wave propagating through space along the z direction. Yet these particles don't seem to be influenced by the wave. They're just staying still at the same location, x naught, y naught, z naught, as time passes. The key to understanding what's happening is to recognize that as the gravitational wave passes, the particles remain at rest in this coordinate system. The emphasis here is on this coordinate system. So when we say that the particles remain at rest, that statement has no intrinsic geometrical or physical meaning. It's a statement that depends on the coordinate system that we've chosen. So what we'd really like to do is compute a proper separation between two of these particles, say between this world line and this world line, and monitor that separation in time. But how would we do that? For example, we could pick an event on this world line and another event on this world line, and then choose a path between those events and compute that proper distance. But what if we chose a different point on this world line, or a different path? So you can see from here that this notion of the proper distance between world lines is ambiguous. It's not well defined. Unless we do something to specify which points and paths we're taking. So it's ambiguous without further input for choosing the paths and points. The points or events on the world lines. I think the best way to supply this further input is to ask, what would an observer see? An observer who's riding along one of these geodesics, what would they see happening to the particles nearby? So to answer that question, we'll choose an observer who's riding right along the t-axis. And construct Fermi-normal coordinates in the neighborhood of this observer, and use the Fermi-normal coordinates to track the motion of the nearby particles. So we'll choose our observer at x equal y equals z equals 0. This is one of the geodesics we computed before. And then we'll construct Fermi-normal coordinates for this observer. I discussed Fermi-normal coordinates in detail in Lecture 10, so see Lecture 10. And there I used a bar to denote the coordinates. So the Fermi-normal coordinates were called x bar mu, and I often used, for x bar 0, I often used tau. So tau is also x bar 0, tau being proper time along the observer's world line. And then the spatial coordinates were just denoted x bar a, where a ranges over 1, 2, and 3. The key result that I showed in this Lecture 10 was that the components of the metric in Fermi-normal coordinates call that g mu nu bar. The components of the metric in those coordinates are just eta mu nu plus terms that are quadratic and higher order in the x bar a's. This result tells us that close to the world line of the observer, let's call the observer O, so close to O's world line, in other words, where XA bar is small, and we can ignore these quadratic terms, then the observer O can use special relativity. They can use everything they know about special relativity to interpret all of the results and all of the physics. And in particular, the x bar a's are just spatial Cartesian coordinates. And x bar 0, of course, is tau, is just proper time for the observer. Now let's recall how Fermi-normal coordinates are constructed. And just for notational simplicity and consistency, I think I'll denote the x bar 0 coordinate, the proper time along the observer's world line, as t bar. So the Fermi-normal coordinates will be t bar and x bar a, and sometimes I'll use x bar, y bar, z bar for these spatial Fermi-normal coordinates. So here's the observer's world line. The observer is O, and the world line is defined in terms of our original space-time coordinates as x mu as a function of proper time along the world line. Proper time I'll denote by t bar. And just to remind ourselves that this is the observer's world line, I'll put a little subscript, script O here for observer. So the forward velocity of the observer is u sub O equals u sub O dot. The observer constructs Fermi-normal coordinates by first picking a time, let's say t bar equals 0, and here's the forward velocity at that time. The observer then chooses 3 spatial basis vectors, E1, E2, and E3, such that these basis vectors are orthogonal to the forward velocity u and also orthogonal to each other and normalized. So if we refer to these 3 basis vectors collectively as E sub a, then we have E sub a is orthogonal to the observer's world line, and also these are orthonormal, so EA dot EB is delta AB. And now the observer defines basis vectors all along the world line by parallel transporting these basis vectors. So define the EAs along the world line by parallel transport. So that's U alpha del alpha E mu A equals 0. As I showed back in lecture 10, if these orthogonality conditions hold at the initial time at t bar equals 0, then they'll continue to hold into the future as these basis vectors are parallel transported. Physically, the way the observer defines these basis vectors is with a set of gyroscopes. The axis of a gyroscope defines a spatial direction, and that direction is parallel transported into the future as long as there are no torques acting on the gyroscope. The main result of this construction is a coordinate transformation between the original spacetime coordinates and the Fermi-normal coordinates. So the original coordinates, x mu, as functions of the Fermi-normal coordinates, t bar and x bar a, are given by x mu of O's world line, and that's a function of t bar, plus the basis vector E a mu, and that's a function of t bar since the basis vectors have been parallel transported along the world line, times x bar a, minus 1/2 the Christoffel symbols, gamma, mu, alpha, beta, and these are evaluated along the world line, so they're functions of t bar, times E alpha a, which is a function of t bar, times E beta b, which is a function of t bar, times x a bar, x b bar. And then there are higher order terms in the x bar a's. Now let's transform our gravitational wave metric into Fermi normal coordinates. So remember, the metric has the form of the flat space-time metric in Minkowski coordinates plus a small perturbation, and the only non-zero components of the perturbation are the xx and yy components, and those are equal to plus or minus a times sine of omega t minus z. So if we put that together, the metric is diagonal, so let me write it this way. Diagonal minus 1, then 1 plus a sine of omega t minus z. The next entry, the yy entry, is 1 minus a times sine of omega t minus z. And the zz component is just plus 1. And remember, this amplitude a is small. Now, our observer O just sits at x equal y equals z equals 0 at the origin in these coordinates. And so the world line of the observer, x mu sub O as a function of t bar, is just t bar comma 0 comma 0 comma 0. And so the forward velocity of the observer is just 1 comma 0 comma 0 comma 0. And now we need to construct these basis vectors, the EA mu's. And because the metric is diagonal, it's pretty easy to guess. We'll take E1 mu to be 0 comma 1 divided by the square root of 1 plus a sine omega t minus z, comma 0 comma 0. E2 mu is 0 comma 0 comma 1 divided by the square root of 1 minus a sine omega t minus z, comma 0, and E3 mu is equal to 0, 0, 0, 1. Now, because the metric is diagonal, you can tell just by inspection that each of these vectors is orthogonal to u, and they're also orthogonal to each other, and they're also normalized. But let's remember, we're constructing a set of basis vectors along the world line where x, y, and z are equal to 0 and t is equal to t bar. So for the basis vectors on the world line, we can replace this combination t minus z with t bar. And this t minus z is t bar. Let's also remember that this parameter a is very small, and we're carrying out all of our calculations just to linear order in a. So let's write these basis vectors to linear order in a. E mu1 is 0 comma 1 minus a over 2 times sine of omega t bar, comma 0 comma 0. E mu2 is 0 comma 0 comma 1 plus a over 2 times sine of omega t bar, comma 0. And E mu3 is 0, 0, 0, 1. Now there's one more condition that we need to check. We need to know that these basis vectors are parallel transported along the world line. So it's possible to have a set of basis vectors that are orthogonal and normalized and space-like. They're space-like with respect to the world line, but they rotate relative to the basis vectors that are parallel transported. In other words, they rotate relative to the directions defined by the inertial gyroscopes. So we need to know that our set of basis vectors is not rotating. So we need to check that u alpha del alpha e mu a is equal to 0. Now this can be expanded in terms of ordinary derivatives and Christoffel symbols to give e mu a dot, the dot is differentiation with respect to proper time t bar, plus gamma mu alpha beta e alpha a u beta. But u beta is just 1, 0, 0, 0, so this is E mu A dot plus gamma mu alpha 0 E alpha A. So let's first consider this basis vector. Let's let A equal 1. So we can immediately compute E1 dot is 0, comma, the derivative of this is minus A over 2 times omega times cosine of omega times t bar, comma 0, comma 0. That takes care of this term. Now let's compute this term. We have gamma mu alpha 0 E alpha A. Now in the sum over alpha, the only non-zero term is when alpha is equal to 1. So this is gamma mu 1, 0 times 1 minus A over 2 sine of omega t bar. So we need to compute these Christoffel symbols. So we have gamma mu 1, 0 is 1/2 g mu nu times partial 1 g0 nu plus partial 0 g1 nu minus partial nu g1 0. Now remember the metric is diagonal, so this term is equal to 0. And also the only non-zero term here is when nu is equal to 0, but g0 0 is just minus 1. So the derivative of minus 1 is 0. And now the only non-zero term here in the sum over nu is when nu is equal to 1. So this is equal to 1/2 g mu 1 times the derivative of g11, but g11 is just 1 plus a sine of omega t minus z. So this simplifies to 1/2 g mu 1 times a omega cosine of omega t minus z. Now let's remember we're evaluating this along the world line where z is equal to 0 and t is equal to t bar. So gamma mu 1, 0 on the world line is equal to 1/2 g mu 1 times a omega cosine of omega t bar. And now we can insert this result in here, and this index a should actually be a 1. And then gamma mu alpha 0 e alpha 1 is equal to 1/2 g mu 1 times a omega cosine of omega t bar times this factor, 1 minus a over 2 times sine of omega t bar. Now let's remember that we're carrying out all of our calculations to linear order in this small amplitude a. And we already have a factor of a here, so this term can be dropped because it just contributes quadratic terms to our answer. And also g mu nu to leading order is just the flat Minkowski metric eta mu nu. So this is approximately 1/2 eta mu 1 a omega cosine of omega t bar to linear order in the small parameter a. Now, of course, eta mu 1 is only non-zero when mu is equal to 1, so let's write our answer this way: 0, comma, 1/2 a omega cosine of omega t bar, comma 0, comma 0. Now we can compare this result to our previous result for E1 dot, and we see that they're just the same but with opposite signs. So the sum of these two terms equals 0. So what we've just shown is that for the basis vector E1, it's parallel transported along the world line. And by a similar calculation, you can show that E2 and E3 are also parallel transported. So we've now confirmed that the basis vectors are parallel transported along the world line. So the EAs are parallel transported. They satisfy U alpha del alpha E mu A equals 0. Now we can put all of this together to construct the coordinate transformation from our original space-time coordinates to Fermi normal coordinates. So here are the basis vectors that we need. And this is the coordinate transformation. This transformation is expressed in terms of a series expansion in the spatial Fermi-normal coordinates, the x bar a's. And for our present purposes, we only need this expansion out to linear order in x bar a. So we only need this part of the expression. So explicitly, this coordinate transformation is given by the following. We have t equals t bar, x equals 1 minus 1/2 a times sine of omega t bar times x bar, y equals 1 plus 1/2 a sine of omega t bar times y bar, and z equals z bar. And I'll remind you that there are higher order terms in the spatial Fermi-normal coordinate. So this is accurate through linear order in the x bar a's. And as always, it's accurate through linear order in small amplitude a. Now let's invert these relations. We have t bar equals t, then x bar equals the inverse of this factor to linear order in a is just 1 plus 1/2 a times sine of omega times t bar, but t bar is equal to t plus corrections, but this is already a small term because of the factor of a, so we can just replace t bar with t here, then times x. And likewise, y bar is equal to 1 minus 1/2 a times sine of omega t times y, and z bar equals z. Now recall from earlier in the lecture that we found a family of geodesics which were given by x equal a constant, x naught, y equals a constant, y naught, z equals a constant, z naught, and t just equals the proper time along the geodesic tau. Using this coordinate transformation, we can write down these world lines, these geodesics, in terms of Fermi-normal coordinates. We have t bar equals tau, x bar equals 1 plus a over 2 times sine of omega tau times x naught, y bar equals 1 minus a over 2 times sine of omega tau times y naught, and z bar equals z naught. Keep in mind that the observer who's sitting at the origin can interpret these coordinates, the spatial coordinates, x bar, y bar, and z bar, as Cartesian coordinates. So the values of these coordinates give the actual proper distances along orthogonal spatial directions, and at the same time is defined by the observer. So what the observer sees is that any particles that are displaced from the origin in the x bar, y bar plane will undergo oscillations with angular frequency omega. However, notice that the oscillations in the x bar and y bar directions are out of phase by 180 degrees due to this sign difference. So, for example, let's take a look in the x bar, y bar plane. So this is the x bar axis. This is the y bar axis. Now here's a test particle on the x bar axis at tau equals 0, so it's at location x bar equals x naught. Now as tau increases, the particle moves outward. So after a fourth of a period, it moves to location 1 plus a over 2 times x naught. And similarly, if we have a particle on the y-axis, during the first 1/4 of a period, it will move towards the origin by an amount minus a over 2 times y naught. We can, in fact, consider a whole ring of test particles. So initially, these particles are spread out in a circle, and during the first 1/4 of the period, this particle will move outward, find them out a over 2 times x naught. This particle will move inward. So the whole pattern, the whole ring, distorts into a ellipse. So this is the ring at tau equals 0, and this is the ring at tau equals pi over 2 omega, which is 1/4 of a period. Then after another 1/4 of a period, the ring returns to its original shape. So this is also the shape at tau equals pi over omega after half a period. Then during the next fourth of a period, these particles all shift in the opposite directions. So the ring distorts into an ellipse that's elongated in the y bar direction. So this is the ring at tau equals 3 pi over 2 omega. And finally, after a full period, 2 pi over omega, the ring returns to the original shape. So this picture shows the physical measurable effect that a gravitational wave has on a set of freely falling unaccelerated test masses. So these are freely falling and therefore unaccelerating test masses. Let me summarize. What I've shown is an example of a gravitational wave. And it was defined by the metric perturbation h mu nu, which was diagonal 0 a sine of omega t minus z, comma a minus a sine of omega t minus z, comma 0. And this is a plane wave propagating in the z direction. And with what is called the plus polarization. The term plus for the polarization comes from the effect that it has on a ring of test masses. They distort into a sort of plus pattern. And another thing that you should notice from this example that's true of all gravitational waves is that the wave is transverse. In other words, the wave only affects the separation between test masses in the plane that's transverse to the direction of propagation. In the next lecture, I'll show how this example is derived and also show that there's another polarization state called cross polarization. So next lecture, we'll derive the plus and the cross polarization gravitational waves.